All right, let's continue. Any questions or comments? Okay. So I want to go through an example to see like a direct manifestation of time dilation and length contraction. Example. So I want to talk about muons. How many people know what muon is? Muon? How many people don't know what muon is? Okay. How many people know electron? Everybody knows electron, right? Muon is exactly like electron. So muon. It's same charge, like same spin, but the only difference is there are actually two differences. The mass, I think, is 200 times heavier. 200 times m electron. Let me write it like this. And its lifetime is much smaller. Like electron is have almost infinite lifetime, whereas muon has a finite lifetime. And we can create muon in laboratory, right? We have technology to do that. We can bombard and smash things, and we can look at the things that comes out from the experiment. One of the things can be muon, and we can look at how long the muon survives. And from this, the lifetime is about 2.2 microseconds. Okay, so these are known. So these are facts known. And another thing that happens is because of cosmic rays, right? Sun is bombarding us with not only the visible light, it's bombarding us with all kinds of stuff. And these cosmic rays sometimes create muons in the atmosphere, right? And also you can do the experiment, right? You can look at different elevations to see where these muons are created. And typically, they are created at 6 kilometer elevation, and they have speed v is equal to 0.998 c. You just, I don't know, take go to Cappadocia, take an air balloon. When you are 6 kilometers, you can turn on your detectors and look at your oscilloscope screen or something like it. It says the speed is 0.998 c, and there's I don't know, some signature of muon, and you know it's the muon. And from the elevation, you know it happens a lot when you're about 6 kilometers. So then the question is, right? So this is okay. This is say this is Earth. So this is Earth. So this is 6 kilometer, and this is muon, and it goes with speed v, which is given here. And the question is, can they reach Earth surface? Okay. Okay, let's calculate. Let's calculate it like this. So, how do I see if something is reaching the Earth's surface? It's moving with velocity v, and it survives a time about 2.2 nanoseconds, right? And the maximum distance it can take, let me call it delta x max, is going to be v times t lifetime, right? What else can I do? It's speed, speed times time is the distance. Speed is 0.998 c, 998 C, and time is 2.2 microseconds. And if you calculate these things, like I expect you to do, in case I ask this in exams or assignments, right? You should probably have like pocket calculator to get it out, punch the numbers. And if you do this, you are going to find 0.66 kilometers, which is less than, actually much less than, like 10, almost 10 times smaller than 6 kilometers. And now the question is, do they reach the Earth's surface? Huh? No, right? Like, they should not, according to this, they should not reach Earth. According to our calculation. However, we can bring that detector we found the muons on the Earth's surface and turn it on and see if that's really the case. And what you are going to find is actually, so this is observation. You see about 1 muon reach every centimeter square every minute. Okay, like for 1 minute, 1 centimeter, which is like something like this. There's like a 1 muon, and like then there's something wrong with like this is like a huge number, right? Wherever you put your detector, you just see muons bombarding you all the time. So then something is wrong here, right? We have to fix this calculation. What is wrong? Can you say one more time? Yes? We didn't count time dilation. How should we do that? But what should I fix here? 6 kilometers is not constant. So this is also a suggestion. So, but let's first think about time. What should I fix about this time so that I fix my earlier calculation? Right now, my calculation is garbage because it doesn't explain the observation. And now I look, it's like 2 lines of calculation. We should be able to fix it. Like we should change only one number in this page as a hint. And we should, huh? Can you say one more time? Lifespan? Lifespan, exactly. Lifetime, right? Why should we change lifetime?
Because since they moving closer to the speed of light,
yes,
they will live longer.
Exactly, right? If you want, you can imagine to be like there's like a clock inside the muon, and that clock determines when it's going to decay. And according to us, right, we are doing the experiment on the Earth's surface. The clock inside the muon is going to slow down, right? If it slows down, it's going to survive a little longer, according to us. And if we do that, okay, fix time dilation. So T is going to be equal to T naught times 1 over 1 minus V squared over C squared. Right, T naught is 2.2 microseconds. V is 0.0998 C, and right, this is a number. You can just put all of these things, and what you are going to find is like this is 34.8 microseconds. And if you put this, right, it's like the now delta x max is going to be equal to V muon times T, not T naught, and this is like 0.998. See, this is 34.8 microseconds. My calculations are generally wrong, but you can check it for yourself. At least for this one I found 10.4 kilometers, and since 10.4 kilometer is bigger than 6 kilometer, this calculation says muon should reach Earth. Good. So that we saved the day with time dilation. But now there is a second problem. What about muon rest frame? Rest frame. So let me draw this picture again. According to muon rest frame, right? I'm in the rest frame of muon. Lifetime is 2.2 microseconds, and I have to cover a distance of 6 kilometers. But I can only go like I calculated here, 0.66 kilometers. Then how do I fix the physics in the muon rest frame? What is the resolution?
Distance is not 6 kilometers.
Exactly, right? Now the distance should be contracted. Maybe here's your optional homework. Use length contraction to see if muon reaches Earth according to its rest frame. Good. So I think it's a nice example that we have to use both length contraction and time dilation, and it's like physical, right? Many things we say like twin paradox, they are like non-experiments, right? They only happen in our head, but this is a real life application. Yes.
Can we say that always when we look from the frame of object which goes nearly closer to the speed of light, we always consider length contraction, but in the case of looking at some object that goes nearly same as the speed of light, we change the time, we look for time dilation. Is this always the case, or can they interchange?
No, this is always the case. I think it takes a little bit time to like settle in your head. The way I memorize this, like moving clocks run slower, moving meter sticks get shorter, right?
No,
like
for this particular example, you looked for time dilation, time getting longer for time dilation for when we look for the observer at Earth, but you looked for the construction for observer of like for in the reference frame of
yes.
Muon, right?
Yes.
So we always look for.
We both look at both ways. Like you can look at whatever way you like. If you want, you can choose any frame, right? Any frame is a good frame according to Einstein postulates. Whether you want to use muon frame or Earth frame should not matter. You should always find the right results, and that's what we did. If we use the Earth frame to fix the result, 6 kilometers is 6 kilometers in Earth frame. There's nothing we can do about that. But the time inside the muon can change because muon is moving according to Earth frame. Whereas if you are in the muon frame, the 6 kilometer is Earth frame 6 kilometer, right? Muon is not going to see that 6 kilometer. It's going to see, because Earth is approaching the muon in the muon rest frame, although it has less time, right, in its own frame, the distance is also less, so it does what it wants to do. Good. Any questions or comments? Yes.
Then if we measure the lifetime of muon with respect to Earth frame, will we measure the 34 seconds?
Yes, that's exactly what we should measure.
Then 2.2 is with respect to
Its own rest frame. If a muon is at rest, like standing in our lab, right, it's going to survive for 2.2 seconds. But if you blast that muon for like almost the speed of light, you can make it live longer. If it's like even higher, you can make it live forever, right? As speed of light reaches as the speed of muon reaches the speed of light, it's going to live longer and longer and longer. Yes. Can you say one more time?
If we observe muon during this period, are we going to see it in slow motion, like its lifetime? Are we going to observe it in slow motion?
No, I mean when we observe, what we observe is like something just is generated in like 6 kilometers, and it moves real lifetime. Nothing slows down, right? In our frame, things move with our frame. It's not like we do like a 0.5 frame, like we don't slow things down. But what happens is like its internal clock, right? Muon's life is determined with the internal structure of muon itself. So muon cannot use somebody else's clock. Muon has to use its own clocks to determine what's going to happen. And that clock is going to look slower to us.
So, like, it's going to live longer clock? Or
Yes, it is going to, it's not going to look longer. It's going to live longer in our frame. Like, there's two things. One muon is, like, suppose created in the lab, it is at rest. The amount of time you'll observe it is like 2.2 microseconds. Like exactly like I answered, if you shoot this muon, like if you create it and then shoot it for like, I don't know, very high speed, it's going to survive a little longer.
is this like a method we use in like making particle accelerators to observe? Or
I mean, it's not a method we use, but they have to account all of these effects. Like particle accelerators, like CERN, they have to live with this. That's, yeah, everything they observe is in agreement with special relativity. And they actually like speed up like particles, and they can never reach v is equal to c. They go like really high speeds, 0.999 something, but it's never 1 c. Okay. So let me give you one more unfamiliar consequence of relativity. And suppose let's think about this train moving with respect to us. So this is the train. This is moving with velocity v. And there is observer A outside. And suppose observer B has got like long arms. He's kind of like Wembanyama, like this. He's got really long arms. And so this is B. And he has like light sources in his hand. One here. Let's call it S1 and S2. And I also assume this observer B has same length arms. I don't know. I think people may have like different length arms. If you are that kind of person, I don't account that. So this is L and this is L. And so he is like standing inside the train, and he just presses the buttons at S1 and S2 at the same time. Right? This is like a light coming from here and light coming from here. Right? I just press the button at the same time, and I ask the question: does the light from source 1 come at the same time to me with the source at 2?
Yes.
Right? Everybody says yes. Right? Any objections? Anybody saying otherwise? So S1 light and S2 light are going to reach observer B at the same time. So because it should either reach me or not at the same time, right? There's no other, like, it's like a true or false experiment. It either reaches to me at the simultaneously or not. So any objections? Okay. Everybody agreed. In a little bit, I'm not going to accept, I mean, if you have objection, yes.
Simultaneity depends on the frame.
We don't know that yet. That's what we are trying to see. At the moment, we don't know. So according to B, if I am B, if you are doing this experiment, it's going to reach at the same time, right? To you, you receive S1 and S2 at the same time. Good. Now let's look at exactly the same experiment from the perspective of A. Right? According to A, S1 and S2 are created at the same time, but the observer B is moving with velocity v. The light coming from S2 is going to have a little bit less distance to cover, right? Because B is moving towards the light, whereas S1 is going to have a little longer distance, right? Because B is moving away from S1. So according to A, S1 is going to be received after S2. Do you agree? Yes?
Are we accepting that the S1 like stays in place and his arms get longer?
No, we are saying that like we are observing it from the outside. S1 does this experiment. In his frame, he just presses the clicks at the same time, and they reach him at the same time. That's what he sees.
Okay.
And now we are expecting we are trying to see what A will see, right? So the question is A going to see these two, S1 and S2, reach at the same time, or is he going to see they reach at different times? And the reason I ask this question is because since V is moving on this direction, right? It is moving towards S2, but it's moving away from S1. So according to A, it looks as if S1 should reach later. Any objections to that? Anybody has any suggestions? Now the question, yes? Yeah, distance, like whether distance shortens or not, it's not the thing, right? I am just comparing the times. I'm just comparing how much time it takes for S1 and S2 to go. Yes, it shortens, it gets blah, blah, whatever. I'm just looking at the picture and I'm saying that S1 should arrive later because S1 is going to have more distance. Whether contraction is there or not, I don't even care about that. Because the source is moving, like the target is moving away from the bullet. Bullet has more distance to cover, right? That's the reasonable thing. But on the other one, the bullet and the target, they move towards each other, according to A, right? Then common sense says this guy, right, S2 should reach B first, and then S1 should reach B. No? Why no?
I don't know.
Uh-huh.
It doesn't.
Yes?
I think the problem is they will not see them, everything at the same time.
Why?
I don't know, it's only
Yes, that's the resolution. So what we say simultaneous in B's frame does not have to be simultaneous in A frame. So what happens is like B receives S1 and S2 at the same time. That's a fact, right? You can like check this, like you can, I don't know, build a bomb here. That's generally how people explain this, but I didn't want to encourage violence. Suppose there's like a bomb that explodes if it receives those signals at the same time. So then the bomb either explodes or not. And if the bomb explodes in the B frame, it explodes in all frames, right? We are not like going to like alternate reality in relativity. We don't have things like this. So if the bomb is going to explode, then the only resolution is like S1 and S2 should be generated. They should be created at this different times according to A. So what B thinks of course B does it at the same time in his frame, but these two simultaneous events, they don't look simultaneous in A frame. Okay, so that's the target. Maybe I can write this. Simultaneity is frame dependent. If something is simultaneous in one frame, they are like spatially separated. They don't have to happen in the same time in all frames. Any questions or comments? Yes?
For example, moving close to speed of light or at the speed of light. Time for them
So B is moving with speed of light. Can you say one more time?
The guy inside.
Uh-huh.
Would run slower for him, right?
It's in the frame, yes, moving frame.
So if time would run slower for him, how?
Time is not uncertain. We don't say time is uncertain.
Right?
You said time is uncertain?
No, time would run slower.
Slower, yes, yes.
So it would not explode simultaneously, right? It would
Mhm.
differ in
Mhm.
frequency.
Yes,
Or
yes,
it would explode
yes.
after.
hmm
How is it?
But like, suppose you are doing this experiment, right? And suppose you have equal length arms, and you either receive them at the same time or they're not, right? You are pressing at the same time, and you either receive them at the same time, or whether time is slower or faster doesn't matter. In your frame, you don't see us. Suppose I cover all the walls, you don't even know you are moving. So equal length and equal speed, because speed of light is speed of light. You go with c, the length L. You go with c, the length L. They take the same time, and if they are generated at the same time in your frame, they should reach you at the same time. Whether time slows down or not is irrelevant, because time slows down for an observer outside. You are inside. Right? That's the problem with.
I get that, but you said that at the instant when it explodes,
Mhm.
it doesn't matter which viewing preferences you are in, it all explodes at the same time for everyone, right?
Oh, I didn't say at the same time. What I said is like either bomb explodes or not. The fact that bomb exploded is a true or false statement. If it's true in all frames. And since we said that it reaches the observer B at the same time, this is a true sentence. It should also reach at the same time for observer B. But for an observer for this sentence to be correct for an observer A, we have to change something. And what we change is like simultaneity. Like the moment S1 is created is not simultaneous with S2. There is no conflict in that. That's how we save the day. Yes?
I was wondering, why is B receiving the two light beams at the same time more factual than B pressing the buttons at the same time?
Yes. I mean, like, it's not fake. Like, this is also like Gedanken experiment. We can do this experiment, right? Like, even if you bring Rambanyana, maybe his right hand is going to create faster a little bit. I don't know. His reflexes are different. So this is a thought experiment. And when I say a thought experiment, we are adults. We do physics by consent. You have to accept this, right? They happen at the same time in your frame. Like in frame B, they happen at the same time. We assume this. Like, can we do this in real life? I don't know.
No,
This is
I'm saying, why is light reaching B also correct at the same time, simultaneously also correct in frame A,
like,
but not pressing buttons at the same
yeah. I don't know. I think it's more like a logic question than like a physics question. For example, this can happen. Like, suppose this person B does this experiment, and right after the experiment takes note. The light reached me at the same time. It's like a note. After the experiment is done, A can go and check, right? Just because in his frame things are a little different, it doesn't mean he's going to find a different note. Like, we can make it more dramatic by a bomb, right? Suppose we build a bomb that explodes if the light reaches at the same time. The bomb explodes or not. Two different people should not see different things.
Okay, what if we build a bomb that explodes if the two buttons are pressed at the same time? Then will it
Yes, then that's fine. That's a bomb. And then what? Yeah, that.
If B presses at the same time in B frame, but in A frame?
But like then that's like a problematic thing, because then you have to devise a non-local bomb, right? Your bomb should know about two locations. A non-local bomb is not easy to, right? There is no such things. Typically, physics is local. What this means is like things happen at a given location. Like there is like a chemical reaction, there's like some radioactivity taking place, but it's taking place in this location. What happens here is dependent only on here, right?
Yeah, I think I understand.
Right? It is. I don't think the kind of bomb you suggest is even possible to build.
Information transfer.
yeah, right. You have to transfer the bomb, the information, like all those things. But the point is, like, simultaneity is frame dependent, right? One thing is simultaneous in one frame doesn't mean it has to be simultaneous in all frames. Good? So maybe I summarize and I finish today. I think we have, yes.
You said that B sees S1, like A sees that B receives S1 later. How is that possible? Like, or did I understand you wrong?
Now, if they happen at different times, right? If they, like, if S2 first signals, right? Now S2 is, sorry, if S1 is out first, right? It is created and it's already on the way. Even if it has like longer distance to cover because B is moving, it has more time. And S is like generated later, right? You created S later. Even if you have less distance to cover, you are not there yet. You have to, like, right? By doing this adjustment, we made everything make sense. Good. Yes?
If you have a system that allows us to press buttons outside the train,
Mm-hmm.
do we have to press S1 earlier than S2?
If you have a device that you can press the buttons inside the train from outside,
Yes.
and can you ask one more time? I think this is the thing about this relativity. Like, there are like frames. Who is with respect to the communication is always a problem. Can you ask one more time? Like,
The buttons are inside the train,
uh-huh.
but we are pressing them outside the train. With such a system, I don't know.
Like a long stick, you just press it, something like this.
I don't know.
Or maybe you throw like a ball.
You have to do something, I don't know.
I don't know how to do that, but I mean,
If you create such a system,
uh-huh.
do we have to press S1 earlier than S2?
But I think this is just a made-up example I imagined to show you simultaneity. Maybe you can do something like that, but I don't know what it means. Yes, if you find something interesting, we can discuss, but you don't take this seriously. But take this simultaneity seriously. Okay? Yes?
We take S1 and S2 are sources, but if we take only one light source at the observer's head,
Mhm.
S1 and S2 are
Receivers?
yes.
Mm-hmm. But like exactly the same problem with, like, now this is non-local, right? We are trying to save the locality. Actually, this is like a stupid example, but I think it's good because we are making everything local. Now, your suggestion and your suggestion, it's like a non-local, right? The reception happens at different times, different places. But in my setup, it happens at the same location and same time. That's a different, like, locality is a different important thing here, ingredient. Okay. Any questions? Okay, we talk about too many things, but let me just make a quick summary. You can think about this. It takes a little bit of time to get used to these things. We have like basically two things, right? Like before these two things, we had Einstein postulates. One was speed of light is c in all frames, and also nothing can go as long as you have mass. Nothing can go with the speed of light. And the second one, physics is the same in all frames. Physics, laws of physics is the same. This is actually something you may like because you don't have to choose frame, right? All frames are good. And if we have these two assumptions, the conclusion was like, I think very like different from like Newtonian and Galilean physics. We had space-time, rather than time and space at different agents. And why do I say space-time? Because time dilates and length contracts depending on the frame of reference. Okay, and also if you combine these two things, there's also simultaneity is frame dependent. Okay, this is the summary I expect you to know. Maybe we can continue next time.